Welcome. This video will be the culmination, at least for now, on my series on functions. In the last video, we analyzed discrete functions where the function values were separated somehow. And in this case, we're going to be doing some more real analysis where we allow the codomain to consist of objects that are infinitely close together. And to represent these objects, I will be using continuous intervals. All right. So I will be doing, I'll be considering functions that go from some interval between two numbers, a and b, into another interval, c and d, c to d. All right. The endpoints do not have to be a part of the set, and the endpoints can also be infinity. This can be all numbers, it can be half of all numbers, it can be any interval you can think of. In theory, the function can also be defined on separate intervals, like you can have an interval here, an interval here. The problem is, when you're doing these kind of analysis, you will always do this separately. You will do the analysis on this interval and then this interval, not both intervals at the same time. There are some small exceptions, for example, if they're really close together. But for now, let's just assume that we have this interval where we're doing the analysis on. All right, so how do we represent a function like this that is defined on a continuous interval like this? Well, we do something very similar to something we've done before. We create a Cartesian coordinate system like this, named after René Descartes. I hope I'm pronouncing that correctly. It consists of a horizontal line like this, directed line because it's increasing in that direction, called the x-axis. And it consists of a vertical line, directed line like this, called y-axis. Right? And what we do now is, well, we put our function, or our domain, on the x-axis, and we put the codomain on the y-axis. All right. And what we do now is we do the same thing we always do. We do a visual representation of our function. And I'm just going to do any arbitrary function. Okay, so let's say it looks something like this. What you noticed is that I've drawn it completely within the codomain. Well, that's because the function lives within the domain and the codomain, so I can't go outside. And how do I read this? Well, if I have any value in here, let's call it t. If I have any value t, the way I read it is, okay, how do I relate t to some value in the codomain? Well, I create a vertical line up here, and I go horizontally with a right angle, and then this value here is going to be f of my value t. This is actually really similar to what I was doing with the books in the previous video, where I drew these lines. It's exactly what I'm doing. I'm drawing a line with a right angle in it. But that's it. You can even put a little line, arrow here if you want. That wasn't that bad. The reason we do it this way instead of the other way is because there are an uncountable infinite number of values here, because it's continuous, which means that I would have to draw so many lines to get this to make any kind of sense. So drawing this graph is actually a much faster way to do that. Okay, beautiful. So we have our function. Wonderful. We have no expression yet, but I don't need it yet. I want to consider what do surjectivity and injectivity look like in this context. All right. So what was it surjectivity was? Well, surjectivity meant that if I take any number element in the codomain, I should be able to connect it to some value in the domain by our function. And what we do is we try to see if we can draw a horizontal line and see if it touches our graph anywhere. And you can see for this value here, it doesn't touch the graph anywhere if I make this horizontal line. That means there's no value in the domain that's connected or related to this value, which means that it's not surjective. I can relatively easily make this function surjective by just removing d down here. And I would actually also have to move c up because there are also some values here that are not really connected. So I would move c up, I move d down, and now my function is actually nicer surjective if I'm interested in that. There's a slight problem with that. Let's say I expand my domain and this graph is actually increasing, then I get outside the codomain and there are some problems with that. But if you're really intent on making it surjective, this is one way you can do it. All right. What about injectivity? Well, injectivity is something similar. We want to see if there are any values in the codomain that are related by two separate values in the domain. Okay? So I can, for example, take this one and put it down here somewhere. No, that's nice. One value, one value. But let's do it over here. Let's do this horizontal line here. Oh shoot, it's connected to this, it's connected to this, and it's connected to this. It has three values at this point, which means that the inverse is multivalued and has three values at some of the points. All right? So it's not injective and absolutely not bijective, which means that our inverse is not going to be single valued. So we're not going to have a nice inverse in this case. Yes. But what does the inverse actually look like? How did I find the inverse when I had my function? Well, in the book case, what I did is I just flipped the whole thing upside down. Instead of going up, I went down from the colors to the books and not the other way around. What that looks like in this case is actually flipping the x-axis and the y-axis. So we do a reflection here about this, about a diagonal that goes through here. Okay, so we flip this whole thing and draw the same relation. It's the same relation, it's just from a different perspective. So let's see, let's imagine that it connects to here. So let's see, how does this look if I flip the y and x-axis? Well, it's going to look something like this. Let's see if I can do this properly. So top, something like this. Not that bad, but could have been better. Maybe it's a little bit shorter. Maybe a little bit flatter. Something like this. Okay? Can you see that it goes up and down and up? This goes up and down and up. All right? So this is what it looks like, approximately. So this is the inverse here. So if this is f, this is f to the power minus 1. All right. So let's imagine that we want to analyze the inverse somehow. Okay, so we can analyze the inverse at different points, and there's no problem here at the start because it's a nice little function, and we can do all sorts of interesting analysis. And the same thing actually at the end here. There's no problem. The problem is where the function becomes multivalued. Again, this is why people don't like multivalued functions. It makes things more complicated, but definitely manageable. And one way to manage this is to create so-called branches. So instead of considering the whole function as a single object, you can split it up into branches and separate functions. Okay, and you can do this in any way you like. Okay, you can, for example, let's look at this problem area. The problem area is really where we have these multiple values. So it's this band here is the problem area. Okay. So how could I define these branches? Okay, well, I can go, okay, so this top part here, that's one branch. And what I can actually do is I can actually just continue it down here. So I can have this branch, this red branch, that is this top part of the inverse and the bottom part of the inverse. That's one way to do it. The only problem here is that this top part and this bottom part don't really seem to have anything to do with each other. There's a huge, it's discontinuous, it's not connected at this point, at this left vertical line here. And they don't even have the same slope. It doesn't seem like they have any common characteristics where they make this little jump here, which feels like it's slightly useless. Okay, so I personally don't like this way of branching it. Another way of branching it that I would prefer is actually to take this top branch here and then make another branch here and then make a third branch here in the middle. So I've turned my multivalued inverse into 3 single-valued branches where each branch is nicely connected and has a nice structure, but they are not really connected meaningfully. All right. So I've chosen to do the branch like this. You can do the branch. You can choose to do the branches another way if you have a more useful way to do it, but it's your choice. It's all about usefulness. What can I use this for? And this might be a weird construction to create branches out of multivalued functions, but there are fields, again, like complex analysis, where creating these branches is completely essential to the analysis. So this is not something I just came up with, but the first time I've seen it applied to arbitrary functions and not complex functions. All right. So that is that. So there's some choice here. Some functions will have an extremely natural way to branch them. For example, let's take another function here. And a lot of people will not call this a function. They'll call this a relation or something. But I have no problem calling it a function. So let's say we have another function here, which is a circle. And there's a beautiful, almost the only meaningful way to branch this is just to cut through the middle. If I just cut this circle down through the middle, I get these 2 branches. One branch up here, and one branch down here. And I would argue that any other branching would be completely meaningless. All right? There are other cases where it's not so straightforward. For example, let's take a function like this. Let's take a function that is just multivalued on the whole thing. So we can do something like this. So this is one function, not 2 functions. That's why it's one color. But it's multivalued, and it's multivalued on the whole domain. It's 2-valued on the whole domain, actually. Okay. So how could I create branches here? Well, I could do something pretty intuitive. I could go, okay, well, I'll just stay on the top the whole way through. It's a totally legitimate way to do this branch. I could just stay at the bottom. Or I can actually do anything in between. I can go here, up, and through, or I can do anything. There is a slight problem here, and I don't know if you see this already. There are these points here where it's really pointy. The graph is really pointy. And what being pointy means in math is that it does not have a nice slope at this point. Like what is the slope? You can intuitively see that it has a nice slope throughout, but until when it gets to this point, it doesn't have a nice slope anymore. Or at this point. And the same thing for the purple. These intersection points create these points where the slope is poorly defined, or maybe not defined at all. Okay? And you can use that as a criteria for you making a nice branch, where the criteria is simply, I want it to be continuous, like up here, and I also want it to have a nice slope. I want it to have nice characteristics. So what I would do is I would take this branch, and I would take this branch, which is actually the way I drew them originally. Because you see, this is a nice function and this is a nice function. But this is just personal choice. There's no rule that says you have to choose these branches. All right. This may seem some just random nonsense, but I would argue that you have probably seen one of these multi-valued functions before. Let's consider the equation x squared is equal to 4. x squared is actually a nice function. It's not multivalued. It looks something like this. All right? And when you're solving this equation, you're looking for x's where x squared is equal to 4. What you're doing here is you're actually taking 4 here, and then you're doing this horizontal line thing. You find two values that have this property, -2 and 2. So what we know here is that x is equal to ±2. What you're really doing here is you're actually finding the inverse. You're finding the inverse. And what does the inverse of this function look like? Well, we talked about this earlier. You need to reflect, you have to flip the x and y axes, which means a reflection in the diagonal there. So the inverse is going to look something like this. And what you're doing is you're going out to 4, and then you're going up and reading the values, which turns out to be 2 and -2. This is a multivalued function. Even if you didn't realize it, you've actually seen multivalued functions before. What we usually do is we just disregard this lower branch. We just say the square root of 4 is 2. Not ±2, it's just 2. But I would argue that it's actually ±2. It's just a multivalued function. The point here, the problem, the benefit here is that you can actually, all the analysis you do on the top branch can just be is completely symmetric with all the analysis you do on the bottom branch. So you don't have to do two separate analyses. You just do the analysis on the top part and then just multiply by -1, and you get pretty much all the characteristics of the lower branch. So here, the way to branch this is completely natural, and you've already done this. Yes. So multivalued functions is a huge and natural part of mathematics, even the mathematics that you are and have been doing. Yes. All right. I mentioned continuity, and I mentioned the slope. And that is going to be the next topic of this analysis. We're going to look at what does it mean to be continuous, what does it mean to have a slope, and a third characteristic that I did not mention yet is actually we're also interested in finding the area under the graph of a function like this. And there is an interesting connection between the area under the graph and the slope. And it's called the fundamental theorem of calculus. And I have proved that in another section. But in the absolute ultimate culmination of this series, I will explain what continuity is. I will explain how to define and interpret the slope of a function like this, and how we construct the area under the graph for one of these branches, and then I will mention the connection that I will prove that I have proved in another section. All right. If you have any questions or comments, leave them below. All right.